So in this video I want to look at another application of derivatives, and that is finding the intervals on which a function is increasing or decreasing, along with finding its extrema. So I have written here on the left a function f of x equals x squared over x squared minus 9. We're told to find the intervals on which the function's increasing and decreasing. So let's think about how we can use our derivatives to solve this problem. The derivative itself is the slope on the curve, the slope of the tangent line at any point on the curve. So if a function is increasing, its derivative at that point is going to be positive, and likewise if it's decreasing, its derivative at that point is going to be negative. And we know from previous experience that when a derivative is zero, that's the extremas where a function changes direction. So we can use that information to find the intervals on which a function may be increasing or decreasing. So first let's go ahead and take our derivative. So here our derivative f prime of x equals, we'll use our quotient rule, so it'll be the derivative of the numerator times the denominator left alone minus the derivative of the denominator times the numerator left alone, and all of that divided by the denominator squared. And when we simplify that, we get 2x cubed minus 18x minus 2x cubed all over x squared minus 9 squared. And you'll see that the 2x cubes will cancel one another, and that simplifies to being negative 18x over x squared minus 9 squared. Now what do we need to do with this? We're looking to find points on which the graph is either at an extrema, at a critical number is what it's referred to, and that's just some point. A critical number is some point on the graph where the derivative is equal to 0, or the derivative is undefined, but the critical number has to be defined on the original function. So if we set this equation equal to 0, our derivative, we know a fraction is 0 when the numerator is 0. So when does negative 18x equal 0? When x is equal to 0. So x equals 0 is a critical number. Now we also have to take into consideration where the derivative is undefined. In this case, our denominator is going to be undefined at plus or minus 3. Well, that's undefined on the original function, so it's not a critical number, but we do need to consider it when we're making our calculations. So we'll say at x equals plus or minus 3, there is a discontinuity. So with that in mind, what we're going to do is set up intervals around these points to test whether the function is increasing or decreasing. So with 3 points, it'll be 4 intervals. We'll have negative infinity up to negative 3, negative 3 up to 0, 0 to positive 3, positive 3 to infinity. And what we're really doing with this is we're saying at 0, negative 3, and positive 3 are points where the graph can change direction, because you can't be increasing and change to decreasing without coming to either an extrema, which we find with those critical numbers, or a discontinuity, an asymptote or something in the graph. So we've found those points where it can change, and we set up intervals, and now we're going to say, okay, if it's increasing on any place in this interval, it has to be increasing everywhere. And if it's decreasing at any place on the interval, it has to be decreasing everywhere. So now the question is, how do we find whether it's increasing or decreasing? We can just plug a number into our derivative, because the derivative is the slope of the curve. So we just need to pick any number within these intervals and plug it into our derivative to see if it's increasing or decreasing. So just pick a number out of convenience. It can't be the endpoints, like negative 3 or 0 or 3, but any number within the interval. So we can say negative 4 for the first, negative 2 for the second, 1 for the third, 4 for the fourth there. When we plug those into the derivative, I ask, what is f prime of negative 4? Well, we know that f prime of x is negative 18x over x squared minus 9 squared. Now if we take a step back and think about it, our denominator is always going to be positive because the entire quantity squared. So we really just need to see when we plug a positive or negative number into our numerator, what do we get? Since we have negative 18 multiplied by x, a negative number makes a positive because it's two negatives multiplied, and a positive number will make a negative because it'll be a negative 18 times a positive number. So f prime of negative 4 is going to be positive, greater than 0. F prime of negative 2 will likewise be greater than 0. F prime of 1 is going to be less than 0, because if we plug a 1 in, negative 18 times 1 will be negative 18. And finally, f prime of 4 will also be less than 0. So with that in mind, we know that the function will be increasing on all numbers or all points on the interval from negative infinity to negative 3 and from negative 3 to 0. And you may say, why do we need to split that into two intervals? There's a discontinuity at negative 3. There's a vertical asymptote there. So to answer the question, we'll say that it's increasing on our intervals that had positive derivatives, which will be negative infinity to negative 3 and negative 3 to 0. And it's decreasing on the intervals where our derivative was negative, which was 0 to 3 and from 3 to infinity. And then I may also ask, what are any extremas on the graph? Well, we can get that very easily from these intervals, because we know as we're going to negative 3, we're hitting an asymptote, so it's undefined on the original graph. It can't be an extrema. But as we go to 0, our function's increasing. When it gets to 0, it changes and it starts to decrease. So if a graph is increasing up to a point, hits the point and decreases, that will be a maximum. So we can say that there is a max at the point x equals 0, and when we plug that into the original function, y equals 0. So by using this first derivative test, we can find the extremas, we can find the intervals on which a function's increasing or decreasing, and get a really good idea of what the graph is going to look like.